All right, let's do this. So today we're going to be discussing IR spectroscopy. All right, we're going to start. All right, today we're going to be discussing IR spectroscopy, IR standing for infrared spectroscopy. I will throw it out there that when I first learned this, I read it in a book and I thought it was infrared for like ever. And it's really hard to get that out of my brain. So I'm sure I'm going to missay it today, but it is infrared spectroscopy, okay? Which I guess you guys used in the lab last semester and they just never really introduced it as a concept. Is that correct? You've used it before? Wonderful. Okay, well now you'll know what you're doing. Okay, cool. So first of all, we're going to pick apart this second word here, spectroscopy, because there are a lot of different experimental techniques that fall under that same umbrella of spectroscopy. And they all do the same thing, but just in kind of different ways. They take advantage of the interactions between photons and atoms. Okay? And that in and of itself is actually pretty cool. The universe is full of a ton of different particles, muons, neutrinos, things you only really discuss in advanced particle physics because we don't really care about them. All right? They're raining down on us right now, and we don't care because they don't interact with what we're made of. Right? We're made of atoms, which are protons, neutrons, and electrons, and not all particles interact with atoms. All right? But photons, they do, and we take advantage of that. They all have the same basic setup. You have some photon source, right? Like a light bulb. And that photon source is sending photons through your sample. Right, so we have our photon source, and it's sending in these photons into our sample. But some of those photons get absorbed by the sample. So not everything that you send in makes its way back out. And on the other side, you have a detector. And that detector will sort of tell you what it is that you got back out on the other side, or more importantly, what was actually absorbed by your sample. Okay, so all spectroscopies have this same basic setup. You've got a photon source, you're sending it through a sample, you're measuring what comes out the other side. Okay? The difference between all the different spectroscopies is that photon source. What exactly photon source are you using? The first one you would have been introduced to was UV vis spectroscopy, where you literally use a light bulb, right? Because now you're paying attention to photons that are in that visible portion of our spectrum. Okay? There are a lot of different photons out there, ranging from X-rays, even gamma rays, all the way to microwave radiation. All right? Our eyeballs can detect a very narrow region of this spectrum here. All right, so this is that little fancy V shape there is for frequency. Or we can talk about photons, different photons as having different wavelengths. These two are one and the same. They're related through that Einstein equation. So if you know one, you can always figure out what the other one is. All right, but they're one in the same way of talking about different photons. So again, what you discussed before is UV vis spectroscopy using this chunk of our spectrum. Our eyeballs can detect this chunk of our spectrum. When we're talking about IR spectroscopy, now we're going to this chunk of our spectrum here. So our light source that we're going to use, our photon source, is going to be sending in photons in this portion of our spectrum, not a portion that we can detect with our eyes. All right, so what do the different portions of the spectrum do? They interact with your molecule in different ways. In UV vis spectroscopy, It is interacting with the electrons in that molecule. All right, so you talked about exciting electrons with your spectroscopy, with your photons. When we're talking about IR spectroscopy, it's not the electrons that are being interacted with, it's actually the bonds themselves. Okay, so what's happening here? You're going to send in a photon. That photon's going to get absorbed by your molecule. What is it doing with that energy? All right, well, bonds, they're always moving about. And when they absorb IR radiation, they start moving about even more, right? You excite those bonds to different vibrational energy levels, right? So the bottom line is your molecule's down there dancing about, wiggling about. You send in a photon in the IR spectrum and it gets absorbed. That energy goes into making it dance that much more frantically, wiggling it about even more, right? You're exciting those bonds so they vibrate even more. All right, so just to kind of summarize here, our IR spectroscopy. We use photons in the IR region. Those photons excite chemical bonds in our molecules. Make them dance around even more. Okay? So why is that useful? It turns out to be something that's very useful in organic chemistry because we divide the world up into different functional groups. Right? How we understand organic chemistry is we group all molecules that have these same bonding patterns into a different functional group category, and we know that all functional groups, they kind of behave the same, or rather all molecules with a given functional group kind of behaves the same, right? So we classify a molecule as an alcohol because all alcohols have a similar property, and alcohols share that OH bond. Right? So the fact that IR is letting us see different chemical bonds means we can use it to identify a functional group in our molecule. All right? And that's kind of what you want to have in mind when you're doing IR, is it helps you identify functional groups. All right? Functional group and IR should be synonymous in your brain. Okay? What it cannot do is help you identify shape or size. Right? So ethanol and octanol, they both share that OH group. They're going to look the same in your IR. Okay? So it's limited in that, yes, we can tell our functional group. No, we cannot uniquely distinguish between molecules that share a functional group. In that sense, IR is quite limited. So then why do we use it compared to some other techniques? Practically speaking, it's super easy, right? If you've done it before, you go over, you put your sample on the machine, you press go, done. You get your IR spectrum. So it's easy to use. The other thing, practically speaking, is it's very cheap compared to other experimental methods. So you can get a nice IR for like 10 grand versus an NMR, which is going to be like $250,000, right? So one of them is way easier to get your hands on than the other one. Okay? We are going to talk about NMR next class period, which is how you would go about identifying shape and size. You get a lot of information from an NMR. It's more of a pain in the ass to use, and it's very expensive. Right? So they're kind of flip side here. This one, not a super amount of information, but easy to use and cheap. Okay, cool. So, like we said, we're exciting bonds. Different bonds absorb in different places of our spectrum. Actually, I lied. Let's just look at a spectrum real quick. Okay? You put your sample on, you press go, this is what it spits out. An IR spectrum. And this is what you analyze to get information about your molecule. All right? The x-axis of our graph is our wave number, or our frequency of our photon. Right? So down here is a different photon than over here is a different photon than over here, right? Again, your photon source is sending in a packet of photons. Each one's got a different frequency. That's what your x-axis represents, is all the different photons that are being sent into your sample. All right? And then it measures what comes back out the other side, your percent transmittance here. IR spectra are a little bit different than other spectroscopies, which like to talk in terms of absorption, so our peaks are pointed up. IR, for whatever historical reason, likes to talk in terms of percent transmittance, so our peaks are pointed down. They're one and the same thing. You can always convert from one to the other, all right? But the bottom line is up here, this would mean that no photons were absorbed. And down here is all of those photons were absorbed. All right? Okay, so again, our photons are being absorbed by those bonds that are starting to vibrate even more rapidly. Turns out that the different bonds absorb at different portions of our spectrum here. So all of our single bonds, or rather all of our large atom single bonds, are down here all the way on the right-hand side of our spectrum. We start increasing in wave number, and that's when our double bonds start to absorb. We increase even more in wave number. That's where our triple bonds absorb. And then lastly, anything bound to hydrogen absorbs in this top part of our spectrum here, all the way on the left. All right? Turns out that something bound to hydrogen absorbs differently from all of our other single bonds because hydrogen's just easier to excite vibrationally. It's so teeny tiny small that it's much easier to excite something that's bound to that teeny tiny hydrogen, to get that bond vibrating even more, all right? So our something bound to hydrogen single bonds on the left-hand side, all other single bonds on the right-hand side. Okay, so how do we go about analyzing our IR spectra here? All right. The first thing that I'm going to do when I get my IR spectra, let me get rid of these, sort of make this more clear. All right, the very first thing that we do to analyze our IR, is we're going to cut it up. We're going to cut into those different regions, right? We said that our different types of bonds absorb in these different regions here. So that's what we're going to do, is just kind of lay down these markers that separate each one of these regions. All right, and we can see that it's really 1600 to 1850, or 23 to 21. I like to use nice round numbers, makes your life a little bit easier. So I remember we cut at 15, 20, and 25. This will roughly divide this up into our single bonds, our double bonds, our triple bonds, and then lastly our something with hydrogen region. All right, so I'm being a little sloppy here. Again, we can note these ranges, but first thing I do is I just cut it up based on those nice round numbers into these different regions here. Okay, the single bond region, we got another name for this here. And we call this the fingerprint region. All right, much like your fingerprint, each molecule gives you this unique pattern in the fingerprint region, okay? It's also not very helpful for us to look at. Just like you can look at two different people's fingerprints and you're like, okay, great. Like, I don't know who's who. All right, kind of the same thing. First thing I do when I get to this fingerprint region is I'm like, no, I don't care. I'm ignoring it, okay? There's always a lot of information there. It's very hard to parse out. It's always just a cluster of peaks all stacked on top of one another. It's a great thing for like a computer database to try to search through to uniquely identify a molecule, not super helpful for us, okay? That's not to say that there's never anything that you look for in that region, but generally speaking, we ignore that region, okay? So in this molecule here, what I would do is I'm going to look now in the double bond region, the triple bond region, and the something with hydrogen region, and I'm going to analyze each one of these peaks, okay? And in this particular spectrum here, I will just say that these two little things down here, they don't actually have any information about them, all right? This is what makes these IR spectrum analysis sometimes a little bit more art than science. No spectrum's like perfect, where there's absolutely no little blip on the graph in your double bond region, but you're also never doing these like in a vacuum. You always have like an expectation of what's going to be in there, right? You've just done a reaction. You know what you started with, you know what you're expecting. So if you're not expecting any double bonds, then you're just gonna ignore that little set of clusters, that tiny little peak in the double bond region, okay? So again, a little bit more art than science. Sometimes our expectations inform how we read our graph, which then informs our expectations, and back and forth and back and forth. All right? So for this particular one, I would analyze these two sets of peaks in my graph here. All right? And what do we mean by analyze? We mean we're looking for 3 different pieces of information. Number 1, the wave number of that peak. Right? So this is where on the x-axis we're looking. The other one is the intensity of the peak. This corresponds to the percent transmittance, the y-axis. Oops. Okay? For intensity, we usually don't put a number on it. Like you could say where you are on your y-axis. Usually we just put it into one of 3 categories. It's either strong, moderate, or weak. Okay? And then lastly, our last piece that we include for all of our peaks is the shape. By that I mean how broad it is. All right, and again, we could sort of quantitatively do so by putting ranges of where that peak starts and where that peak stops. But again, generally speaking, when they're talking about shape, they're not talking about a number. They're again talking about like a qualitative tag that you give to it. So a shape is either narrow, medium, or broad. All right, so again, you kind of throw it into one of those 3 buckets. Okay, so let's say that I was analyzing this big peak right here. I would first give its wave number, or in this case, it's probably a little better to do a wave number range here. We'll call this 31 to 36. I think they actually go the other way, 36 to 31 inverse centimeters. All right, this has that pretty strong absorbance, right? A very low percent transmittance means a lot of those photons were absorbed. So I'm going to go ahead and call this a strong peak, and it's also relatively broad. All right, so that would be my analysis for this peak here. My wave number range, the 36 to 3100, it's strong and it's broad, right? Those 3 pieces of information are what you're going to put on each peak in your graph. Okay, just to kind of illustrate here, again, wave number is where it is on the x-axis. The intensity, this is kind of your 2 extremes here. Actually, this one's probably even more of a medium compared to this one, which would be strong. All right, and then breadth of our peaks, this would be a very broad peak compared to this very narrow peak. All right, so those 3 pieces of information are what you put on each one of your peaks in your graph. Cool. All right. So now we're going to go through and talk about these different bonds that you would, what signal would you expect to see for different bonds, okay? And this is kind of how you want to be thinking about your IRs. It's more like pattern recognition than anything else, right? By the end of the semester, you'll know what an OH bond looks like in your IR, right? You'll know what that kind of peak looks like. Okay, so first we're going to talk about carbon-hydrogen bonds. This is a great place to start because by definition, an organic molecule's got to have one. All right? We got three different types of carbon-hydrogen bonds. So first of all, where are these carbon-hydrogen bonds going to absorb in my spectrum? So fingerprint region would be for our larger molecules. Remember, something bound to hydrogen is a special type of single bond that always sits far out here on the far left of your spectrum. All right? So that's where our carbon-hydrogen bonds will live. And there's one cluster of peaks that you're going to kind of always see. There are three different types of carbon-hydrogen bonds that we could have depending on the hybridization of that carbon. So if your carbon's got all single bonds, it's sp3 hybridized. If your carbon's got a carbon-carbon double bond, it's sp2 hybridized. And if it's got that carbon triple bond, it's sp hybridized. All right? And each one of these different carbon-hydrogen bonds absorb in a slightly different place on our spectrum. Okay? This one right here, you will almost always see. Okay? If you just like drew 12 random organic molecules on your paper, chances are each one of them has a lot of sp3 hybridized carbons with hydrogens on them, right? So we see this peak, or rather cluster of peaks, in just about every IR spectrum that we see, all right? And it looks something like this, always around 2850 to 3000, okay? Importantly, it stops at that 3000, which is something that turns out to be really helpful. It's always a cluster of medium and strong peaks, and there are many narrow ones kind of stacked on top of one another. So it always is like this little jagged cluster of peaks right here. Okay? In our previous example, we talked about this big broad peak that I colored in green here. We also have this one here, and that corresponds to those carbons and hydrogens, specifically those sp3 hybridized carbons and hydrogens. All right, so you'll see that cluster in like every spectrum that you look at. Okay, one more helpful thing that we do, we said that we cut up this spectrum into these different regions here. All right, it turns out to also be pretty helpful to lay down one additional one here in the middle of this something with hydrogen, and that's around 3000. All right. Your carbon-hydrogen, specifically sp3 hybridized carbons and hydrogens, will always sit just south of that 3000 marker. Okay? If you have any carbon-carbon double bonds, so if you have any sp2 hybridized carbons with hydrogens on them, they will absorb slightly higher than 3000, so a little bit above that extra marker that you just laid down. And if it's a carbon-carbon triple bond with a hydrogen, it's going to be even further up. All right, so we lay down this extra line here at 3000 to help distinguish between our alkanes and something that only has carbons and hydrogens single bonds, and say an alkene, where we're going to get an additional peak above that marker. All right, so now we have one just above 3000. They tend to be medium to strong. I don't know, they actually can be pretty weak, but always very narrow. And if we had an alkyne, we get another one, but it's even further up. So now we're around 3,300 medium to strong and narrow. Okay, so in addition to cutting up our IR spectrum into those different bonding regions, we also lay down one more at 3,000 to help us distinguish between an alkane, or an alkyne. All right. If I do have an alkene or an alkyne, I would also expect something in the double bond or triple bond region of my spectrum. All right. So for example, if we took, this is actually an overlay of two different molecules here. In blue, we have one octene. And in red, we just have octane. Okay. If I'm going to cut up my spectrum here, again, 1,500, 2,000, 2,500. And then we're going to lay down that extra one at 3,000. Again, just kind of using nice round numbers. This separates into our fingerprint. This is our double bond portion, our triple bond portion, and then our something with hydrogen portion of our spectrum. All right. If we look in the fingerprint region, great, we do have something unique, but again, we largely just ignore that fingerprint region. Importantly here, on my blue graph, I see this peak in the double bond portion of my spectrum, corresponding to that carbon-carbon double bond. But I also see this extra little peak just above that 3,000 marker, corresponding to my sp2 hybridized carbon with its hydrogen. All right, so my alkene, we see that extra thing above that 3,000 marker, but we should also see our carbon-carbon double bond in our spectrum as well. All right, same thing if we had an alkyne, we would expect to see a peak in that triple bond portion of our spectrum. All right, going through the functional groups now. Alcohols, specifically talking about that hydroxyl group. This is an incredibly IR active functional group here, a very easy one to spy on an IR spectrum. Okay, so this right here is our spectrum for ethanol. All right. What does this cluster of peaks correspond to? The carbon-hydrogen, the one that we always see. All right, so this is my carbon-hydrogen bonds, specifically those sp3 hybridized carbons. We always see a little cluster like that in our spectrum. Our hydroxyl group is this bond right, this peak right here. So that alcohol functional group, that hydroxyl group, has this characteristic bond in our something with hydrogen region. Okay. Tends to be between 32 and 3,600 and is a nice strong peak that is also characteristically broad. Okay. So whenever we see a nice broad peak in that 32 to 36 region, that's going to correspond to an alcohol. And yeah, one of the easier functional groups to spy. Okay, another really easy one to spy are carbonyls. Carbon-oxygen double bonds. All right, what region is that going to fall in on my spectrum? That double bond region. Okay, so indeed a carbonyl. This is an example to butanone. We lay down our markers here. Okay, and then that extra one. Again, this is the fingerprint region that we ignore. Here in my double bond region, I get my carbonyl bond. All right, so this here corresponds to that carbonyl bond, always around 1700, and they're they're like reliably very strong and narrow. Okay. If we get a carboxylic acid, where would we expect to see peaks in our IR spectrum? All right, here's a carboxylic acid. Where are we going to expect it to absorb in our IR?
More than 3,000.
So which bonds in particular can we see?
The double bond.
So we got this double bond here. We should be able to see, what else can we see in this molecule? The OH group, right? So your carboxylic acid is going to be a combination of those two that we saw. All right? There is actually a distinguishing feature of the carboxylic acid hydroxyl versus an alcohol. First of all, we still get that strong narrow peak around 1700 corresponding to our carbonyl. All right? And we get that broad peak, but in the case of a carboxylic acid, it's actually a very broad peak. So broad that it ends up swallowing up that carbon-hydrogen set of peaks as well. Okay? So it's different from an alcohol where there's a little bit of daylight between those two clusters of peaks. A carboxylic acid is as if this peak sort of moved over and was laid on top of that one as well. All right, so for our carboxylic acid, okay, we get this even wider range from 2200 to 3600. So a very broad peak, strong, and importantly, very super extra broad. Okay? And again, we can kind of note, so broad, it's merged with our carbon-hydrogen peak. Specifically that sp3 hybridized carbon-hydrogen peak. Okay, and the last functional group that we're going to talk about identifying patterns for are amines. Amines are these nitrogen-containing functional groups. All right, so an example would be this one here. What makes amines a little bit more of a broad class is different from, say, how we distinguish between alcohols and ethers. They call it an amine regardless of where that nitrogen appears in the molecule. So for example, I could have that nitrogen sandwiched between two carbons. This is still an amine. Or it could even have 3 carbons bound to it. This is still an amine. All of these fall under that same umbrella as being an amine functional group. Okay, we do distinguish this first one we would call a primary amine. The second we would call a secondary amine with 2 carbons bound. And if there are 3 carbons bound to that nitrogen, we call it a tertiary amine. All right. Now, one of these I'm not actually really going to be able to see very well on my IR. It's not a very IR active functional group. All right? That's because all of its bonds that are will fall in the fingerprint region except for that sp3 hybridized carbon-hydrogen bond that we always see. All right? Which one of these isn't going to be IR distinguishable? Tertiary. The tertiary amine, right? The other ones all have a bond that I am going to be able to spy, that nitrogen-hydrogen bond, right? That'll absorb in my something to hydrogen portion of my spectrum. Tertiary means they don't have it, so again, everything's going to fall in the fingerprint region or that cluster of peaks we always see. Okay? And we can actually distinguish between primary amines and secondary amines. First of all, we can note that This is a zoom in of that something to hydrogen portion of my spectrum with that extra at 3000 marker laid down. Okay. Our amines, they absorb just about where alcohols do. It's a very similar portion of the spectrum to where alcohols absorb. All right, 3350 to 3500. They tend to be of medium intensity. And with a primary amine in particular, you get these two broadish peaks here. Okay, and I will say, in my experience, this is a particularly pronounced amine peak. They tend to be more on the weak to medium side. All right, this particular example is a little bit more intense than I feel like what you're used to seeing. Okay, but again, you actually get two broadish peaks for a primary amine, different from a secondary amine, which again absorbs in just about the same region, our 3350 to 3500 region. Again, kind of weak to medium intensity. But now we only get one broadish peak for that primary amine. Secondary amine. All right, so a primary amine has two hydrogens bound to it, and we get those two broadish peaks. A secondary amine has just one hydrogen bound to it, and we get one broadish peak. Okay? So the reason for that, again, what are you doing when you're sending in this IR radiation and it's getting absorbed by your sample? You're exciting those bonds so they bounce around, they vibrate, and there are just two different ways in which a primary amine can start to vibrate. It can start to vibrate symmetrically, where those two hydrogens are moving symmetrically, or it can do so asymmetrically, right? So those molecules put on two different types of dances down there, which is why we see our two different peaks for a primary amine. Cool. All right. So now we're going to do a little bit of practice here. All right, we have two spectra, and we have these 6 possible choices for our molecules here. Let's do this spectrum F first, because this is an easier one. All right. If we're going for the speed record here, what molecule do we think we got in spectrum F? That alcohol peak should jump out to us, right? So this broad peak in that 32 to 36 range is our alcohol. Okay? Let's just kind of convince ourselves, go the long way here. First thing I do is I cut it up into these different regions. I'll put down our extra marker at 3000. We can see, since we ignore the fingerprint region, we don't have any double bonds or any triple bonds present. What does this cluster of peaks correspond to? Carbon, hydrogen, the one that we always see, right? So our defining feature here is this broad, intense peak, again in that like 31, 32 to 36 range. So yes, that's our alcohol. Oops. All right, this one's a little bit trickier. So I'm going to lay down my markers here. Okay. I want you to take a minute and see if you can't identify which functional group we have present here. Okay, if I ignore my fingerprint region, all right, my double bond region, I have this little thing here, that is probably nothing. So don't have any double bonds. I do have this nice sharp peak in my triple bond region. All right, so right there we can kind of distinguish that this would be which molecule? All right, so this must be this one here. We also have one more defining peak here. All right, we got this boring one because we always see it. Our sp3 hybridized carbon and hydrogens. But what does this peak over here correspond to? This is my something with hydrogen portion of the spectrum. Okay. This is also a carbon hydrogen peak, but it's that sp hybridized carbon in my triple bond. So it's very specifically this bond right over here on the end that's absorbing over there as well, right? So remember, your alkenes and your alkynes, not only should you see something in the corresponding double or triple bond region, but also that different hybridized carbon is going to absorb differently with its hydrogen that's bound. Cool. All right. We're going to do one more here. All right. So everybody take a second for these two here. Let's distinguish. All right. Take a second and see if you can't match up each of these spectra to one of the molecules. All right, let's go to this top spectrum here. Ignore that fingerprint region. My double bond region. I have this pretty sharp one over here, pretty weak, but still pretty distinguishable from my baseline. I have this cluster over here that we always see, and then I have this additional one. So first of all, A through F, what do we think this one corresponds to? Anybody got a guess? So this would be A. So we got our double bond here. And again, one of the distinguishing features of that carbon-carbon double bond, so this one would be my carbon-carbon double bond, is that we also get that carbon-hydrogen bond, because we got that sp2 hybridized carbon, right? That sits just north of that 3,000 marker that we laid down. That's why we put down that 3,000 marker, to distinguish between alkanes, alkenes, and alkynes. I will note that there is another functional group in this same molecule, right? It's also an ether. Where does my ether bond absorb in my IR spectrum? Yeah, my fingerprint region, which is why that would not be a very IR active functional group, right? An ether would be hard to distinguish from an alkane. So in this particular molecule, even though it's got these two functional groups, only one of them are what I'm going to be able to see in my IR, right? That's the only one I can really look for. The other one's lost in this mess over here. All right. Our last one here, again, we're going to ignore this. We get a very strong, very narrow peak in our double bond region. And so what does that very strong, very narrow peak correspond to? So yeah, so specifically this would be that carbonyl bond, right? Our carbon-oxygen double bond. So right there I can go through and nix just about all our options except for these two here. All right? So now I'm trying to figure out whether I have a ketone or a carboxylic acid, both of which will have that carbonyl peak, right? But I will be able to tell the difference because of that hydroxyl bond. right? That should also be present in the IR spectrum of a carboxylic acid. And remember that hydroxyl bond is similar to an alcohol, but it's even broader. So much so that it ends up merging with that cluster of peaks that we always see. And so yes, in green here, this is my hydroxyl peak, and then my peak that I always have, my sp3 hybridized carbon hydrogens. So yes, this spectrum here would correspond to that carboxylic acid. And again, I can distinguish between D and E because of the presence of that hydroxyl group. There should be that extra peak in my something with hydrogen portion of my spectrum. Cool. All right, so just to recap here, when we do IR spectroscopy, we're going to use these photons in the IR region. It's going to help us identify different functional groups. And again, each functional group just has this pattern where they absorb in a specific region with a specific intensity and a specific shape. And that's how we go about distinguishing our functional groups in IR. Cool.